Hi everyone, this is Mrs. Marsh, and we're going to start off with a trigonometry review. Now everything in this video is something you should have seen before, probably in trigonometry and then again in pre-calc, but it may have been a little while since we've gone over this stuff, so hopefully this video and the accompanying homework will help you out. So we're just kind of refreshing skills here. The first idea we're starting out with is the difference between radians and degrees. And these are just different ways that we can describe any angle we might have. Any angle can be written in either radians or degrees. And we have this identity here that says that pi radians is equal to 180 degrees. This allows us to just go back and forth between radians and degrees. And in calculus, generally, we're going to see the use of radians a lot more frequently. So we'll start off by using this identity for a few practice problems. First, we're given 330 degrees. Now, if I want to convert that to radians, then I'm going to need to multiply this by either pi over 180 or 180 over pi. I should say really 180 degrees. Okay, so I'm going to multiply this 330 degrees by one of these fractions. Now, which one do I multiply it by? So see, we want this to be in terms of radians. Essentially, we want to get rid of these degrees. And so to get rid of these degrees, I know that I'm going to need this degree symbol in my denominator. You can kind of think about this in terms of units. If I want to get rid of a unit in the numerator, when I then multiply it, I'll have to put that same unit in the denominator. So that's what we do. Because this is in degrees, to get from degrees to radians, we'll multiply by pi over 180. This will cancel out our degrees and leave us with a fraction. So this will leave us with 330 pi over 180. Our degrees canceled out. Now we're just in the business of simplifying this fraction. Now 330 over 180, the first thing I'm going to do is I'll divide by 10, and I'll write this 33 pi over 18. All right, and is there anything that goes into 33 and 18? Well, I can see that 3 goes into both the numerator and denominator. Dividing by 3, that leaves us with 11 pi over 6. And so 330 degrees is 11 pi over 6 radians. And sometimes you'll see this written as 11 over 6 pi. It does not matter. All right. 400 degrees, well, we're going to do the same thing. We'll multiply by pi over 180 degrees. So we've got 400 degrees times pi over 180 degrees. Our degrees get canceled out. We are left with 400 pi over 180. Let's divide by 10. To give us 40 pi over 18. And let's see, what's the largest factor of both 40 and 18? That's looking like 2. And dividing by 2 will give us 20 pi over 9. Now with radians, the important thing here is you just want to simplify this fraction. So we've got 20 pi over 9 radians. So now to go in the other direction, now we're given radians and we want degrees. And something to notice here is that radians, sometimes you'll see this RAD at the end of it just to tell us that we want this in radians, but a lot of times you won't see any kind of unit attached. This will just have a pi in it and it will have no degree symbol. That's how you know that it's not in degrees. If there's no degree symbol, then it must be in radians. So given an angle measure in radians, negative 9 pi over 2. Now if we want this in degrees, then we know out of these two fractions, well, we want the one with the degree symbol in the numerator because we want to keep that degree symbol. So now we've got negative 9 pi over 2, and we are multiplying that by 180 degrees over pi. And when I multiply, let me just simplify my fractions a little bit before multiplying across. So 180 is an even number. I can just call that 9, and I can call this a 1. We can just simplify on the diagonal to make our lives a lot easier. We know these pi's are going to cancel out, and then we are left with negative 9 times 90, which is negative 810 degrees over 1. And so this is just going to be negative 810 degrees. And all this negative does is it just tells us that we're traveling this clockwise. We know that if we have any kind of positive angle measure when we're talking about our coordinate plane, we are going counterclockwise. When we have a negative angle measure, we're traveling that clockwise. All right, one more example. We have 5 pi over 8. We know we are multiplying this by 180 degrees over pi. We know our pi's will cancel out. We can simplify this 180 and this 8. We can, we can divide this by 4. 180 divided by 4 is 45. And 8 divided by 4 is 2. All right, we've got 5 times 45 over 2. And 5 times 45 is 200 plus 25, so we've got 225. All we have left is our degrees over 2. And when we talk about degrees, generally we will write our degrees in the form of a decimal. And in this case, that's a clean decimal. So we get 225 divided by 2 is 112.5 degrees. So we have 112.5 degrees. All right. So now that we've talked about how to convert from degrees to radians and from radians to degrees, let's look at this as it relates to our unit circle. So now we have our unit circle. And we have our unit circle in angles, and what we're going to do is for each of these angle measures, we're going to write that angle measure in radians. So we said on the previous slide that pi radians is equal to 180 degrees. All right, we're going to use this to just fill in our unit circle. Now we know that if we have 0 degrees, well, that's the same as 0 radians. And now what about 360 degrees? Well, pi radians is 180 degrees. So we see that over here. We know 180 degrees is pi radians. And like we said before, with radians, we don't need a unit. This is just going to be in terms of pi in our unit circle. And so if pi is 180 degrees, well, we know that 360 is just 2 times 180, so we're going pi and then another pi, and so that gives us this angle measure of 2 pi. And so at 0 degrees or 360 degrees, we're going to say this is either 0 or 2 pi, however you want to see it. Okay. And so now what about our other angle measures? Well, we know that this 90 degrees is halfway between 0 and 180. So I can just call that halfway between 0 and pi, which is pi over 2. All right, and in the same way, 270 is halfway between pi, and I'm going to call it 2 pi because we're going around the circle counterclockwise. Halfway between pi and 2 pi is 1.5 pi, and we're going to call that 3 pi over 2. And all the measures, when we talk about radians in the unit circle, they're just going to be simplified fractions. Okay, now how about this 45-degree angle? Well, we're going halfway between 0 and pi over 2, so that's going to be 1/4 pi, or pi over 4. And I'm looking at this symmetry in the unit circle. Now I can see that 45 degrees is halfway between 0 and 90. In that same way, 135 degrees is halfway between 90 and 180. And so halfway between pi over 2 and pi is going to be 3 pi over 4. Now I'm looking at my 225 degrees, halfway between pi and 3 pi over 2 is going to be 5 pi over 4. And halfway between 3 pi over 2 and 2 pi is going to be, there should be a box here, is going to be 7 pi over 4. And you'll notice that wherever we have a reference angle of 45 degrees, and this reference angle is going to be the angle from wherever our measure is to the x-axis, we have this reference angle of 45 degrees, we have a denominator of 4, and we see that pattern. Now what about 30 degrees? Well, how do we find out? So in this case, we're going from 0 to 30, so that's a jump of 30 degrees. From 30 to 45 is a jump of 15 degrees. From 45 to 60 is a jump of 15. And then from 60 to 90 is a jump of 30. So just be careful here. This is drawn, while not exactly to scale, but fairly to scale here, that there's a much smaller distance between 45 and 30. Now, if this red line here was directly between 45 and 0, then we know this would be pi over 8, but it is not. And so to find out what this angle is in radians, let's just use our little conversion here. So for 30 degrees, if we have something in 30 degrees, we know we're going to need to multiply that by pi over 180 degrees. And so this is going to give us 30 pi over 180. Well, 180 divided by 30 is 6. And so we can call this pi over 6. So this is going to be pi over 6. If this angle measure is pi over 6, remember, when we're talking about a positive angle measure, we're going counterclockwise. When we're talking about a negative angle measure, or we're subtracting any angle measures, we're going clockwise. And so what that means is that to get to this 330 degrees, well, we know that the distance between 360 degrees and 330 degrees is 30. And if I'm going from 0 to 30 degrees, I'm adding pi over 6. If I'm going from 0 or 360 degrees, I should say, to 330, I'm subtracting pi over 6. And I'm thinking, well, what's 2 pi minus pi over 6? Well, that's the same as 12 pi over 6 minus 1 pi over 6, which will give us 11 pi over 6. Okay, and let's do the same thing over here, because again, we know that this reference angle, the angle between 150 degrees and 180 degrees, is 30. And because I'm going from this 180 clockwise to 150, I'm taking pi and I'm subtracting pi over 6, and I know that's going to give us 5 pi over 6. Going from 180 to 210, because we're going counterclockwise, we are adding pi over 6, and pi plus pi over 6 is 7 pi over 6. So now for our reference angle of 60 degrees. So I see that 90 degrees is pi over 2. To get from 90 to 60, we are going clockwise, meaning we are taking this pi over 2 and subtracting 30 degrees, which we know is pi over 6. So pi over 2 minus pi over 6. Well, pi over 2 is really 3 pi over 6, and so we are left with 2 pi over 6, which is equal to pi over 3. So we've got pi over 3. In the same way with this 120 degrees, if we add pi over 6 to pi over 2, well, that's really 3 pi over 6 plus pi over 6, which is 4 pi over 6. And we're always going to simplify our fractions and call that 2 pi over 3. For this 240 degrees down here, well, we can either go pi plus pi over 3. We can go 3 pi over 2 minus pi over 6. However we want to find this angle. So if I do pi plus pi over 3, which I think is a little easier, we get 4 pi over 3. 300 degrees. I'm thinking, okay, what's 2 pi minus pi over 3? Well, that's 5 pi over 3. And you'll notice this pattern here. So whenever we have a reference angle of 30 degrees, and a reference angle means this angle to the x-axis of 30 degrees, you'll notice we have a denominator of 6 in our radian angle measure. Reference angle of 30 degrees, denominator of 6, reference angle of 30 degrees, denominator of 6, and same thing over here. And you'll notice that pattern with 45 degrees. A reference angle of 45 degrees always gives us this denominator of 4. And finally, a reference angle of 60 degrees always gives us this denominator of 3. And so we can use this pattern. The reason I wanted to just kind of go through it and show us how to get each angle measure in radians is because sometimes we might forget. Sometimes we might forget exactly where 5 pi over 6 is on our unit circle if we don't memorize this whole thing. And this way we can figure out where any angle measure is on our unit circle just based on these 4 major measures that we know of: 0 or 2 pi, pi over 2, pi, and 3 pi over 2. So by just knowing that, if you kind of followed this technique we're going through, you can figure out where any angle measure is on the unit circle. So now that we've gone over all of the angle measures in our unit circle, we're going to start to look at our coordinates. So now we've got the coordinates of our unit circle. And the definition of a unit circle states that we have the circle centered at the origin of our coordinate plane with a radius of 1. And that will give us these 4 points: 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Now, we don't have everything labeled here, but because this is our standard unit circle, this first angle is going to be 30 degrees, or pi over 6. This angle is going to be 45 degrees, or pi over 4. And this angle here is going to be 60 degrees, or pi over 3. Okay, and these are just going to be all of our standard angles that we saw on the previous slide. So with that, we're going to find our coordinates. Now, there are different ways to do this. So we're just going to start off with these 3 different side lengths that we have here, and we'll see these repeat all the way around this unit circle. Our smallest side length is going to be 1/2. Our middle side length is going to be √2 over 2. And our largest will be √3 over 2. And aside from at these 4 points that lie on the axes, we are going to just see these lengths as each of our coordinates in this standard unit circle. And I'm looking at pi over 3. And here I see that if I drew a triangle, so if I drew a right triangle, with this right angle here, then I know that the length of this triangle is longer than the width. And so what that tells me is that in the x direction, I am traveling this largest length of √3 over 2. And in the y direction, I'm traveling the smallest length of 1/2. If I look at the second triangle here, formed by pi over 4 or 45 degrees, well, I can see that I have an equal distance, because if this is a 45-degree angle, this is a right angle here, if you can kind of see that triangle, then this must also be a 45-degree angle right here. And what that tells me is that my two side lengths are going to be √2 over 2 and √2 over 2. And so my coordinate is going to be √2 over 2 and √2 over 2. Finally, at my angle of 60 degrees, we have a triangle. And each of these triangles can just be formed by connecting this point to the x-axis at a right angle. Now, if this large angle is 60 degrees, then by this triangle sum theorem, then this smaller angle must be 30 degrees. And so the length from the origin to this point in the x direction must be that smallest length of 1/2. And in the y direction, it's going to be that larger length of √3 over 2. Okay. Now once we have this, and we could find these using the special triangles, and we're going to look at that on the next slide. Once we have these 3 different coordinates, now we know we're in quadrant 1 right now. We have these 3 different coordinates, and we talk about the symmetry of this unit circle, and so we can use these to label our coordinates on the other side. Particularly this point right here has the exact same coordinates as this point, with the exception of the sign of the x value. So this point is going to have coordinates negative √3 over 2, 1/2. This point will be negative √2 over 2, √2 over 2. And this point will be negative 1/2, √3 over 2. This will be for our points in quadrant 2. So now for quadrant 3, this first point, now this is going to have the same coordinates as these points above, with the exception that now the y value is also going to be negative. And so this point right here is the same as this point right here. And so we can call this negative √3 over 2, negative 1/2. This point's going to be negative √2 over 2, negative √2 over 2. And this point right here is going to be negative 1/2, negative √3 over 2. And finally, in the fourth quadrant, stay in Roman numerals here. In the fourth quadrant, we can get these points from the first quadrant or from the third quadrant. I'll just use them from the first quadrant. Now only our y value is going to be negative. And so this first point is going to be the same as this point, with the exception of our y value being negative, and so we're going to have root 3 over 2, negative 1/2, root 2 over 2, negative root 2 over 2, and this point right here is going to be positive 1/2, negative root 3 over 2. All right. And so if you want to use all of these for a reference when we do these first few problems until you just kind of see that pattern. In general, we have the same set of points. Quadrant 1, both of our x and y values are positive. So I'm just going to say that quadrant 1 is a positive and a positive. Quadrant 2, we have a negative x value and a positive y value. Quadrant 3, we have a negative x value and a negative y value. And quadrant 4, we have a positive x value and a negative y value. And so what is this used for? Well, this can be used to find the sine, cosine, and any of the other different trig ratios of any angle. We're just using the unit circle as a tool to determine the trig ratios of any kind of standard angle. All right, so remembering that our goal is to look at the trigonometry here, and our unit circle is a tool to do that. We're just going to talk about the different trig ratios that we know and love. And hopefully none of this will be new to you. If it is, please let me know. But if we have a right triangle, so we have our right triangle trig ratios. We have a right triangle. We've got what's called our reference angle. Then we know that the sine of that reference angle, and I'll just use theta to denote this angle, the sine of this reference angle is equal to the opposite over the hypotenuse. It's equal to this fraction of the opposite, which I'll just call O, over the hypotenuse. The cosine of theta is equal to the adjacent side over the hypotenuse. The tangent of that reference angle is equal to the opposite side over the adjacent. And then we have our other angles here. We have cosecant of theta, and cosecant of theta is just 1 over sine of theta. And because we're just flipping this fraction of sine of theta, it's just going to be the hypotenuse over the opposite side. Secant of theta is equal to 1 over cosine of theta. And so we're just flipping this fraction for cosine, and that's going to be the hypotenuse over the adjacent side. And cotangent of theta is just 1 over tangent. And this is going to be the adjacent over the opposite. So here are our general 6 different trig ratios. I like to use SOHCAHTOA to remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If we have these first 3, we know that the second set of 3 is just sine, cosine, and tangent flipped. Some people use some old hippie came a hoppin' to our apartment. There are other different ways that you can memorize these. The next method here is using our special triangles, which we're going to see on the next page. So let's look at that. So these are our special triangles. We call this our 30, 60, 90 triangle and our 45, 45, 90 triangle. And with these two different triangles, we can get all of these different coordinates, really. We end up getting different versions of these coordinates to find the different trig ratios of an angle. All right, the next method is the 1, 2, 3, 3, 2, 1 method. So what that looks like is I'm going to write sine and cosine. All right, and I've got my three standard angles. I've got 30 degrees or pi over 6, got 45 degrees or pi over 4, and 60 degrees or pi over 3. And what I'm going to do is I'm going to write 1, 2, 3, 3, 2, 1. And what I'll do with each of these is I will put them over 2 and take the square root of the numerator. Now the square root of 1 is 1, so I won't need to list that. We've got the square root of 2, the square root of 3, and I know that really with each square root I have that positive and that negative option. And doesn't this give us our three regular standard side lengths for every triangle that we could form in the unit circle? We have 1/2 root 2 over 2 and root 3 over 2. And I can use both of these. So say I want to find the cosine of pi over 6, which I know is 30 degrees. Well, I'm going to first look at this special triangle. The cosine of pi over 6 means that this is my reference angle, 30 degrees. And I know cosine is going to be the adjacent over the hypotenuse. So that's equal to the adjacent over the hypotenuse, which is root 3 over 2. If I, for example, wanted to find the cosine of pi over 6 using this little 1, 2, 3, 3, 2, 1 down here, I would just say, okay, pi over 6, I'm looking for the cosine, boom, that's root 3 over 2. All right, if I want to find, and I want to talk about this one, the sine of pi over 4, which is 45 degrees. In this triangle, so using this triangle, it does not matter which of these angles I use as my reference angle. Yes, this triangle isn't exactly drawn to scale. In reality, these side lengths would be the same. But the idea here is that if we have 45 degrees as this reference angle, our sine is going to be the opposite over the adjacent, 1 over root 2. Well, our chart down here says the sine of pi over 4 is root 2 over 2. And you might think these are different values, but they are not. This is just the version in which the denominator is rationalized. So if we take 1 over root 2 and multiply it by a fancy form of 1, like 2 over 2, root 2 over root 2, we are not changing the value of it because this fraction is equal to 1. We can multiply anything by 1. Great, and this will just give us root 2 in the numerator. And root 2 times root 2 is just a regular 2 in the denominator. Now, WebAssign does not have a preference as to whether you rationalize your denominator, so it will take 1 over root 2 or root 2 over 2. So WebAssign does not care. And in calculus, while it's a useful skill to rationalize the denominator, and we are going to be doing that in this course, it doesn't matter as far as your trig ratios go. All right, let's look at some more examples. All right, so to find all 6 trig ratios for 5 pi over 3, I will need to use the coordinate plane because I really want to see where 5 pi over 3 is in terms of my coordinate plane. And more specifically, we're going to use the unit circle. All right, that is a circle. So I want to find out where 5 pi over 3 is on my unit circle. I know I'm starting at this 0. I can also call this 2 pi. I know we've got pi over here. I know we've got pi over 2 up here. And we've got 3 pi over 2 down here. So where is 5 pi over 3? So which quadrant is it in? Well, I know that 5 pi over 3 is greater than pi. I guess pi is kind of like 3 pi over 3. Now, is it larger than 3 pi over 2? Well, 3 pi over 2 is kind of like 1.5 pi. 5 pi over 3 is kind of like 1 2/3 pi. So I know 5 pi over 3 is larger than 3 pi over 2. So I know that this is in fact going to be in quadrant 4. We'll just put a check mark in quadrant 4 to show me that it's going to be somewhere in this 4th quadrant. But where exactly is 5 pi over 3? Well, I'm thinking, how can I get to 5 pi over 3 from 2 pi or from 3 pi over 2? And I think it's a little bit easier from 2 pi. Well, I know that 2 pi is kind of like 6 pi over 3, right? If I take 2 pi and I subtract pi over 3, I can get to 5 pi over 3. When we talk about any kind of subtraction in the unit circle, that means we're traveling clockwise. When we're talking about an addition or a positive value, that means we're traveling counterclockwise. So to get to 5 pi over 3 from 2 pi, I need to subtract, traveling in the clockwise direction, pi over 3. Meaning that pi over 3 is our reference angle. And so what that also means is that 5 pi over 3 is the direction if I travel from this point around the unit circle counterclockwise. So this is 5 pi over 3. And my reference angle is pi over 3. And what I'm really doing is I'm creating this right triangle. Kind of creating this right triangle here with the x-axis. And let's blow this triangle up a little bit bigger so we can label all our sides. All right, we know that this reference angle is pi over 3. And I know that if I have this triangle, all right, and let's look back at our unit circle because we know that this length is 1. I know that our radius is 1, meaning our hypotenuse is 1. So I'll just label that just because we use the unit circle method. I know that my length in the x direction is going to be the smallest of those 3 different standard side lengths of our triangles. And the smallest of those is 1/2. Because we're in the 4th quadrant, I know that my x value is positive because we're going to the right, and our y value is negative because we're going down. And this length in the y direction is going to be the largest of those 3 side lengths, so √3 over 2. And so I'm just going to label this little triangle we've got down here, meaning that this length is 1/2. And now, we know that lengths cannot be negative, but because we're talking about this distance in the negative direction, I'm going to call this negative √3 over 2. Because using this triangle and using this SOHCAHTOA idea, this idea of our different standard ratios, we can find all 6 trig ratios of 5 pi over 3. So, well, we know sine is going to be opposite over the hypotenuse. Because the hypotenuse is just 1, we just have the opposite side length and our sine is going to be negative √3 over 2. Our cosine is the adjacent side over the hypotenuse, so the cosine of pi over 3 is going to be 1/2 divided by 1, which is just 1/2. Our tangent is going to be the opposite side over the adjacent. So we're going to have, we need a little more work here, negative √3 over 2 divided by 1/2 All right, when I take negative root 3 over 2 and I divide by 1/2, I'm sort of multiplying that by 2 over 1 because we remember fraction division is multiplying by the reciprocal. So times 2 over 1 gives me negative root 3. So our tangent is negative root 3. Our cosecant, we said, is just the sign flipped. And remember that we're not picky about whether or not we rationalize the denominator. So cosecant is negative 2 over root 3. Generally, if we have a negative, we're going to just place that negative in the numerator. And secant is 1 over cosine, meaning that we're flipping 1/2, and we get a secant of just 2. Finally, our cotangent is just we're flipping tangent. And because this negative root 3 is the same as negative root 3 over 1, our cotangent is going to be negative 1 over root 3. So this is kind of using the coordinates method. Now, while you'll still have to find out where 5 pi over 3 is in terms of the unit circle, just to find out what's positive and what's negative, you can use some of these other methods like special triangles. This is a very popular method. And how do we do that? Well, we know we have a reference angle of pi over 3. And let's take, for example, the cosine of pi over 3. If I wanted to draw a special triangle and I'm taking the cosine of pi over 3, then I'm looking at the cosine of 60, which is the adjacent over the hypotenuse. So this gives us 1/2 as well. Using this 1, 2, 3, 3, 2, 1 method, that's a little more simple. The cosine of pi over 3 is 1/2. The only thing that you'll have to remember is that neither of these methods include the sine, so just be extra sure that anything that includes the y value is negative, meaning your sine, cosecant, tangent, and cotangent are going to be negative, so just be careful with that. All right. 17 pi over 4. So let's find out where this lies on our unit circle. So 17 pi over 4, I know we've got 0 and 2 pi. We've got pi over here. And if I start here, right, I'm starting at 0, and I make 1 revolution around the unit circle, that brings me to 2 pi. All right? Now 2 pi I know is kind of like 8 pi over 4. If I do a second revolution around this origin, that'll bring me to 16 pi over 4. And so now that I'm at 16 pi over 4, how do I get to 17 pi over 4? Well, I just go up pi over 4. All right, and I know now that my reference angle is pi over 4. So we know that we are in quadrant 1. In quadrant 1, my x and y values are both positive. Great, makes life just a little bit easier. And I know at pi over 4, so that's at 45 degrees. I think about it that in terms of this right triangle. I know that the length and the height of this triangle are going to be exactly the same, meaning I'm going to have this coordinate of root 2 over 2, root 2 over 2. And if I wanted to draw this triangle, just a little bit bigger so we could label our sides. I know because this lies on the unit circle that our hypotenuse is 1. I know we've got a height of root 2 over 2 and a width of root 2 over 2 with our reference angle of pi over 4. And the sine of pi over 4 I know is the opposite over the hypotenuse, so that's going to be root 2 over 2. The cosine is going to be the adjacent over the hypotenuse. So again, root 2 over 2. The tangent is going to be the opposite over the adjacent. So what's root 2 over 2 divided by root 2 over 2? Well, anything divided by itself is just 1. So we're going to have a tangent of 1. Our cosecant is just the opposite of sine. It's just sine flipped, the reciprocal of sine, I should really say. And so that's going to be 2 over root 2. Secant is the reciprocal of cosine. Again, that's 2 over root 2. And what's the reciprocal of 1? Well, 1 is really 1 over 1. So if you flip that, it's still 1. All right? And we have our 6 common trig ratios. Again, you could do this with your special triangles. You could do this with your 1, 2, 3, 3, 2, 1 method. One more thing to point out here is that I see that my sine, well, let's use this other example. Here, I know that this coordinate is 1/2 negative root 3 over 2. I see that my sine is negative root 3 over 2 and my cosine is 1/2. And if we have a hypotenuse of 1, which we do anywhere on the unit circle, I know that the cosine is just going to be this x value and the sine is really just going to be this y value. All right, so let's not forget that. So now negative 8 pi. This negative tells us that we are now going clockwise around the unit circle. So we're going to start here on the positive x-axis. We go once around the circle. We're at negative 2 pi because we're going clockwise. Again around the circle, negative 4 pi. Again around the circle, negative 6 pi. And one more time around the circle until we get to 8 pi, negative 8 pi. Now this tells us that the point we're looking for is right here. And if we're talking about the unit circle, meaning that we have a radius of 1, I kind of draw this point on our unit circle. It's supposed to be a circle. We know that this coordinate is 1, 0. And in this case, we can't really draw a triangle. There's no triangle to draw because our reference angle is just 0. We're just at this point 1, 0. And so our trig ratios, our sine, we can just say that we're taking the sine from this y value, as we determined from the slide, the previous slide, that our sine is going to be this y value of 0. Our cosine is going to be this x value of 1. And if you want to think about this in terms of a triangle, it's kind of like a triangle with a height of 0 and a length of 1. So you can think about it that way too. Tangent, we know tangent is sine over cosine. It's one of our major trig identities, that tangent is equal to sine over cosine. And so our tangent is 0 over 1, which is 0. Cosecant is the opposite of sine. So if we flip 0 upside down, well, what's another way we can write 0? We can really write 0 as 0 over 1, right? 0 over 1 is 0. If we flip 0 over 1, in fact, if we flip 0 over anything, this will give us a cosecant of 1 over 0. And what happens when we have a 0 in the denominator? Well, this is undefined. So our cosecant is undefined. Our secant is when we flip cosine. The reciprocal of 1 is just 1. And our cotangent is when we flip this tangent, the reciprocal of 0. Again, the same idea that 0 over 1 flipped is 1 over 0. And so our cotangent is also undefined. And so these are our 6 trig ratios for -8 pi. So now we've given 3 different examples of how to find the trig ratios for any angle. All right, so let's see where we can use these practically. All right, and before we do that, we just have a master list of general identities we should know. So we should know these generic 6 different trig ratios. All right, we know that tangent is sine over cosine. Cotangent is cosine over sine. We know that cotangent is just the reciprocal of tangent, so we could figure it out that way. Now these over here are called the Pythagorean identities. And these can be really helpful too. Over to the right, we've got the half angle identities. And the half angle identities aren't seen as frequently. We've got our double angle identities to the left. All right, and particularly, we should know the Pythagorean identities, these 6 trig ratios. We should know that tangent is sine over cosine, which would lead to this cotangent here, and we should know the double angle identities. These double angle identities, if you don't have them memorized yet, copy this stuff down and try to see if you can remember it in your homework, because you will not be given any of these on exams. All right, so number 1, sine of x is equal to -1/2. So we want to find all x values in the interval from 0 to 2 pi for which this is true. So I want to find all these angles, we're going to call x in this case, that give us a sine of -1/2. So if I'm thinking about this in terms of a unit circle, well, sine being negative, that means our y value is negative. So that means this can be in the 3rd or the 4th quadrant. And I know that I have a sine of 1/2 at the angle, the reference angle of pi over 6. So I know that if I go down pi over 6, my sine will be 1/2. And if I go down pi over 6 over here, again, I will have a sine of 1/2. So to actually get to these points, so what are these angles? Well, we know that this is 0 or 2 pi. We know that this is pi over here. And to get to this angle here, I'm thinking, okay, what's 2 pi minus pi over 6? Because I'm going from 2 pi in the clockwise direction, and 2 pi minus pi over 6 is 11 pi over 6. Now to get to this angle here, we have pi, and we're going in the counterclockwise direction, pi over 6. And when we travel counterclockwise, that means we're adding. So we're taking pi over 6 plus pi, and that's going to give us 7 pi over 6. Number 2, 3 times the tangent of x squared is equal to 1. And if you saw this little exponent magically change values, it's because I realized my typo at the start of this problem. So I cannot even begin to guess what value of x might make this statement true. So we're going to isolate this x. Specifically, we're going to try to isolate this tangent of x if possible. And I'll begin that by dividing both sides by 3. So dividing both sides by 3, we get the tangent of x squared is equal to 1/3. Now the tangent of x squared, just a little side note here, When I see this notation with the exponent between the trig identity and the variable, this is exactly equal to the tangent of x, that quantity squared. So just keep in mind that when we see this, this is not tangent squared times x, this is the tangent of x squared. And with that in mind, how do we get rid of the fact that this is squared? Well, we can take the square root of both sides. And so we've got that the tangent of x is equal to the square root of 1/3. However, remember, when I'm solving an equation and I take the square root of both sides, I know a negative times a negative is a positive, and so I know that this is really a positive or a negative square root of 1/3. Because if you square a negative root 1/3, you get a positive 1/3 still. So we have tangent of x equals positive or negative square root of 1/3. And I can rewrite this as the square root of, because when I take the square root of a fraction, I'm really taking the square root of the numerator and the square root of the denominator. Now the square root of 1 is just 1, so I can rewrite this as a positive or negative 1 over the square root of 3. Now this doesn't look like one of our basic angle identities. It's kind of hard to tell what tangent is, because tangent, if I think about this in terms of a unit circle, tangent is not my x or my y value. Tangent is the y value divided by x. It's sine divided by cosine. So I'm going to go about this a different way. I'm going to use that 1, 2, 3, 3, 2, 1 method to try to figure out what values of x might give me a tangent of 1 over root 3. Because I want to know what reference angle this is going to be true for. If I know the reference angle, then I can apply it to the different quadrants. So I know with my 1, 2, 3, 3, 2, 1 method, I've got sine, I've got cosine. I know my three basic angles are going to be pi over 6, pi over 4, and pi over 3. I know I'm going to write this 1, 2, 3, 3, 2, 1. I'll divide everything by 2. And put a square root around all the numerators, not putting a square root around 1 because I know the square root of 1 is just 1. And in each of these can all be positive or negative, but I'm not going to write a positive, negative next to all of them. So again, I know tangent is sine over cosine, all right? Tangent of any angle theta is that sine of the angle over the cosine of that angle. Now when I divide fractions, we said that dividing is kind of like multiplying by the reciprocal. I want to get to 1 over root 3, and I'll look at that angle of pi over 6. My question is, if I take 1/2 and I divide by root 3 over 2, is that going to give me 1 over root 3? And I'm going to do that until I find what gives me that correct value. So 1/2 divided by root 3 over 2 is kind of like 1/2 times 2 over root 3, which is 1 over root 3. So great, the first one that we tried gave us that value we were looking for. And so we know that the correct reference angle is going to be pi over 6. And we have this positive or negative, and our tangent can be positive or negative in any of the quadrants. So we're actually going to have 4 different values of x that make this statement true. And again, a reference angle is just the angle to the x-axis. So if I have this angle, this reference angle of pi over 6 here, I can't really write pi over 6 in all of these, but if I'm going up pi over 6, well, I know that this angle is really just going to be pi over 6 because it's 0 plus pi over 6. If I've got an angle of pi over 6 in the second quadrant as my reference angle, then I'm taking pi And going clockwise, I'm subtracting pi over 6, and that's going to give me 5 pi over 6. An angle, a reference angle of pi over 6 in the third quadrant is, okay, I'm taking pi, and now I'm going counterclockwise, so I'm adding pi over 6. That gives me 7 pi over 6. In the fourth quadrant, I have a reference angle of pi over 6, and I know this is 0 or 2 pi, so I'll start at 2 pi and subtract pi over 6 because I'm traveling clockwise, and I get 11 pi over 6. So this is going to make my final answer x is equal to, and we've got all 4 of these different angles, again, because our interval is 0 to 2 pi, so we're saying, okay, what are all the angles that are possible one revolution around this unit circle? And so we've got pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. We need all 4 of these for our answer to be correct. Okay, so we've got one more of these. The sine of x is equal to the sine of 2x. Now here's where those identities come into play. Let's look back at this list of important identities. Well, this looks like a double angle identity, which tells us that the sine of 2x is equal to 2 sine x cosine x. So we need this identity to break this apart. All right, and so we can rewrite this as the sine of x is equal to 2 sine x cosine of x because of that double angle identity. All right, and now what do I do with this? So one thing we might be tempted to do is just cross off sine from both sides, divide both sides by sine. But what that would do is that would potentially remove one of our values of x. So because these are two different functions, we've got a sine times cosine and a sine, we're going to treat this sort of as we would a quadratic. And solving it in that way, we're going to get everything over to one side and set this equal to 0. So adding or subtracting sine from both sides. We get 0 is equal to 2 sine of x cosine x minus sine of x. All right, and because I have a sine in both of my terms, I can factor out a sine. And so we've got sine of x times 2 times cosine of x minus 1. And now using our zero product property, and again, zero product property states that if I have two things that are multiplied, and I'm saying that two things multiplied gives me 0, I'm saying that either one of these, if set equal to 0, would also give us 0, because we know that 0 times anything is 0. So if sine of x was equal to 0, great, that would make this statement true. If 2 times the cosine of x minus 1 is equal to 0, great, that would also make this statement true. So solving these separately, my question is, where does the sine equal 0? Well, I know that sine is our y value, and our y value is 0 at either 0 or 2 pi, or at pi. And because my instructions tell me that to include both 0 and 2 pi, now be very careful. On WebAssign, if one of these has parentheses around them, that means that that is the value you do not include. Because both of these endpoints have brackets, we need to include both 0 and 2 pi. So I can say that this will yield x is equal to 0, pi, and 2 pi. All right, what about 2 cosine of x minus 1 is equal to 0? Well, little more work over here. By adding 1 to both sides, I get 2 times the cosine of x is equal to 1, dividing by 2. Cosine of x is equal to 1/2. All right, referring back up to my unit circle here, where is cosine positive? Well, cosine is positive in the first and in the fourth quadrant. And what reference angle gives me a cosine of 1/2? So an x value of 1/2, well, I know that that's a reference angle of pi over 3. And so this angle is just going to be pi over 3. And now in the fourth quadrant, if I have a reference angle of pi over 3, that means I'm taking 2 pi, I'm subtracting pi over 3, and I'm left with 5 pi over 3. And so for this factor, x is going to be equal to pi over 3 or 5 pi over 3. And because any of these 5 different x values is going to make this statement true, we have to list all of them in our solution. So we get x is equal to 0, and I'll just put them in order. 0, pi over 3, pi, 5 pi over 3, and 2 pi. All right, so we talked about the reason that we kind of solved this problem with factoring. If you look right up here, if we had just divided each side by sine of x, we would just be left with 1 is equal to 2 cosine of x. And we would only get the solutions from this factor. We would be leaving out 0, pi, and 2 pi. That's why it's especially important that you treat this like a quadratic and don't just go kind of crossing off our different trig functions as we might with the method for solving a linear equation. So just be careful with that. All right, so that is it for your trig review. I hope you enjoyed this video, and if you have any questions, please let me know. I am happy to help. Thank you for watching.